All right, we're starting Unit 6, which is our linear systems unit, and starting with graphing. A lot of what you see in sections 6.1 and 6.2 will be review from Algebra 1. And we're starting with graphing, which should be your easiest section of this. It does say at the top of these notes that you will need a graphing calculator. That is not true. So you will be fine without that. Please take a nice big pen and line right through that because you will not need a graphing calculator for that. So a linear system consists of two or more linear equations. So this means first degree equations, so just x to the first. The solution of a linear system is the x and y values that satisfy each equation simultaneously, meaning that whatever solution you find, that x and y coordinate must be a solution to both equations. One way to find the solution is by graphing both equations and finding where they intersect. Please note, they won't always intersect, so there's not always a solution. We'll talk about that as we go on in the chapter. Before you start graphing this equation, I want you to go ahead and we're going to count these by twos. -2, -4, -6. That will work out much better, won't it, Ray? One of my little freshies, Ray, is helping me do my notes today. So, one of the easiest things that you can do is to write both equations in slope-intercept form, because we all know how to graph in slope-intercept form. And the way you do that, the two steps are to move the x term and change its sign. And the second is divide everything by the coefficient in front of y. Divide everything by coefficient of y. I'm abbreviating that. So let's take our first one. We have y plus x equals -1. So we're going to move that x to the other side and switch its sign. We'll get -x minus 1. So if we graph that line, we have an intercept of -1. If it's -x is the same thing as -1x, we go up 1 and over 1 to the left, or you can go down 1 and to the right 1. So there's our line for our first equation. Then we'll take the 6y plus 2x equals 18. Ray, when I move that 2x to the other side, does it stay the same sign or does it switch signs? It switches signs. So we have what? 6y equals -2x plus 18. Then what do I do? Divide everything by 6. Good. So now the slope-intercept form of that equation would be y equals -1/3 x plus 3, because of course you are going to simplify anywhere that you can. And so that would look like having an intercept here at 3, and then we would go up 1 over 3, do it again, up 1 over 3, or we would go down 1 over 3 there, and our line would look something like this. And that point where they intersect would be our solution. What is that point, Ray? Let's see. If it should be a -6, I think I graphed over too far. Oh, that's why, because we should go here. Sorry. As usual, I can't hit my lines very well. Okay, so that point should be -6, +5. And you can always take your solution and plug it back into your original equations to make sure that it actually does satisfy both equations. So, Ray, what's our y value? 5. And what's our x value? -6. And what's 5 minus 6? -1. So that one checks out. What is our y value? Times 6. And what's 2 times -6? -12. And what's 30 minus 12? 18. And that checks out. I will tell you that graphing, for obvious reasons, is not the most accurate way of finding your solution to a system, but it is a useful way sometimes. Okay, so your steps are you're going to write both equations in slope-intercept form. And there are your two steps for doing that. Standard form, to slope-intercept form. Then you're going to find the coordinates of the solution. Then you're going to check your solution by substituting the coordinates back. And when we check our equations, Ray, do we have to check one equation or both? Both equations, because it must satisfy both. Good. Okay. And back into the original equations. And then write your solution as a coordinate point, always. So you're always going to find an X and a Y. Okay? So let's do a couple practice problems down here at the bottom. So Ray, do you want to change these into slope-intercept for me first? So what's going to move first? The 4x is going to move. Is it going to stay positive or go negative? So then we would have 3y equals negative 4x minus 3. Then what do we do? No, oh, sorry, that's still in that one. Do we have y by itself? Divide everything by 3. Good. So then we would get y equals negative 4/3 x minus 1. Let's do our second equation. Actually, we can go ahead and graph that. So where would I begin? At negative 1 is going to go uphill or downhill? Downhill, so we're going to go down 4 and over 3, or we could go up 4 and over 3. Yeah, I'm actually able to connect the dots these days. It's a little bit better. Okay, let's flip our second equation around. So what's going to move? Okay, is it going to stay positive or switch signs? Switch signs. So we have negative x plus 6, and then what do I do? Good. So then we would get y equals negative 1/3 x plus 2. So we start at 2, we go down 1 over 3. Oh, I did it again, didn't I? Up 1 over 3 or down 1 and to the right 3. There we go. There we go. Even we teachers have to check ourselves sometimes. So Ray, what does it look like the solution to that equation would be? Negative 3 and 3. Good. And then we're going to go ahead and check our equations. And that's a quick check. So what's 4 times negative 3? Negative 12. What's 3 times 3? What's negative 12 plus 9? Negative 3. So that one checks out. What is our x value? What's 3 times 3? 3 times 3? 9. Minus 3. 6. That one checks out. Yes, it is late on a Friday afternoon. It's all good. Good. Okay. Those of you watching the video, do example number 3 on your own, and then you can come back and check your work against mine. Okay, so that's how I have mine graphed out. Where's that solution going to be? Looks like it's going to be at... Oh, close. About 7, negative 1. Yeah, those squares are a little smaller on that one than the one before. And we can still go ahead and check our work and make sure. So I'm going to do it down here so we've got some room. What's 3 times 7? 21. What's 7 times negative 1? Negative 7. What's 21 minus 7? 14. That checks out. That matches our first equation. Second equation, what's 5 times 7? What's negative 7 times negative 1? 7 plus 35? 42. So that checks out. Good deal. Okay, and so I decided, just like we did that one time before, that you don't really need to hear me for the whole second part of this. So I'm going to play a little Metallica in the background while you're working on your graphing. And you can watch what I'm doing, but I'm not going to speak for the next 7 minutes. And James and Lars and Kirk, and they'll all sing for you because it's a 7.5-minute song, so it's just about right. Here we go. Okay, so we are actually going to stop at that point. This solving algebraically we're doing in the next section, so you don't need to worry about that. Don't forget that if the lines are parallel, think about if two parallel lines ever cross. Do two parallel lines ever intersect? No, they don't. Then there is no solution. If the lines are in fact the same, they're two lines that actually lay on top of one another, then there are an infinite number of solutions. When we go over this in class, we'll talk about that a little bit more. All right, that was 6-1. Thank you, Ray. On to 6-2.